we're going to draw a distinction between empirical formulas and molecular formulas. A molecular formula refers only to covalent compounds. And that's because a molecular formula tells you the number and type of atoms that are in one molecule of that compound. For example, if we look at all of these compounds, we see that they have different molecular formulas, different formula weights, but they have the same empirical formula. So even though they have this different numbers of carbons, hydrogen, and oxygen in each molecule, the ratio of carbon to hydrogen and oxygen is always the same. There's 1 carbon to 2 hydrogens to 1 oxygen. So this is how the molecular formula can be different from the empirical formula. The molecular formula tells you how many you have of each type of atom in one molecule of a compound. The empirical formula is the lowest whole number ratio of atoms. So all of these different compounds have the same empirical formula and a different molecular formula. The general protocol to determine empirical formula is grams of each, moles of each, mole ratio. We'll look at it in a little bit more detail. Grams of each, here we have the mass of each element. From the mass of each element and its atomic weight, we can calculate the moles, and then we can get to a mole ratio. The simplest way to get to a starting mole ratio is divide by the smallest number of moles, and then you may need to use multiply by some small number to convert to the lowest whole numbers to get to the empirical formula. So it's grams of each, moles of each, mole ratio. Let's go through an example. In this problem, we're given the percent by mass of 3 different elements, and we want to calculate the empirical formula. Starting point, we assume we have 100 grams of the compound, and that immediately converts from percent of each element to grams of each element. Remember, percent is parts per 100, so if something is 29.8% potassium, 100 grams of the compound contains 29.8 grams of potassium. This is what is meant by percent converts to grams. We assume we have exactly 100 grams, so we know immediately how many grams we have of each element. Now we want to calculate moles of each element using each element's atomic weight. As we've done many times before, we're going to divide the mass of the element by the element's atomic weight, such that units of grams cancel, and we're left with moles of each element. I'm going to go ahead and do that math. So we've done our division. We have our moles of each element in 100 grams of the compound. It looks to me that this is a 1:1 to 2 mole ratio, but let's suppose that it wasn't obvious. And our hint here is to divide by the smallest number of moles. So we're going to divide each of these results by the smallest number of moles. And this often leads to a final answer, but not always. In this case, when we do our math, we see this is a 1.0 to a 1.0, and this is a 2.5. What this means is that we have, for every mole of potassium and chromium, we have 2.5 moles of oxygen. Now, we can't use fractions in any of our chemical formulas. They're always the lowest whole number ratio. So in order to get to the lowest whole number ratio here, the easiest thing is to multiply each of these coefficients by 2. So we get K2 CR2O5.